Hello, ladies and gentlemen. Whoops, let me get another pen color, not yellow because you won't be able to see it. There we go, purple. Today we're going to talk about electron and orbitals, and this is going to be a little bit of a long lecture, about 15 minutes, so make sure you take notes and be very careful about what we're talking about today. And so with an electron, we're going to talk about a little bit more about what an electron is. We know it's a very small particle. Very, very small. It's got what we call negative charge on it. The mass is 1/2000th of a Dalton. Very, very small. And it actually moves very quickly for its size. In fact, it moves 1/1000th of the speed of light. So let's put this into numbers. Speed of light is 2.99 times 10 to the 8th meters per second. If we take 1/1000th of that, the speed is 2.99 times 10 to the 5th meters per second, which is equivalent of saying 2.99 times 10 to the second kilometers per second. That's fast, guys. That is very, very fast. And what we have is that's traveling so far. Now think about this. It's traveling that fast, and it's going around an atom which has a very, very small diameter. From our point of view, from our perspective, these atoms are solid. Because the electron, even though it's very small, it's going to hit every place of that sphere that it moves around, every part of that surface area in a second, or less than a second. So it feels solid to us because we can't differentiate the difference between something, where the electron is and isn't, because it's just going too small and too fast. And so what we have is a very, very small electron going very, very fast with a lot of energy. And so when we look at, okay, we got this electron, we know we can take it off. We know it has energy, and it kind of absorbs energy as well. But there is also another principle that means we can't find the electron. And that is a gentleman named Heisenberg said he came up with this uncertainty principle. And he realized through doing some mathematical calculations that the error finding a momentum times the error finding a position cannot be less than 5.263 times 10 to the minus 35 kilograms meters per second squared, meters squared per second. And so let me rephrase this. So if we know exactly where the electron is, and we look at its error, the error in finding the energy of that electron, or the velocity, is so large it can go from 0 to almost the speed of light. So we don't know what the velocity is. And conversely, if we know the velocity, know the energy, if we know the energy of that electron, which we do to a very good precision, with very little error, the resulting error of position is actually about a couple of atoms big. So knowing this, it means that we unfortunately don't know about how to figure out what's happening in the atom of that electron, because our way we measure things gives us too much error. We're limited by the error of the other method. We're limited by error. And so, what else about electrons? They move in waves, hypothesize. And this is de Broglie's theorem. We move in waves. It has an amplitude, has a wavelength, and I'm not going to tell you any more about that because that's for if you continue on in chemistry. But electrons these charged particles move in wave. Now, if you have something something charged that is moving, it's going to have a magnetic component to it. And so the electron is basically heavier than light, but it also has a magnetic electronic component. And these things, if they do have a magnetic electronic component, they're affected by magnetic electrical fields. And we know that happens. We've done experiments on that. So, summarize, we know electrons move very fast in a wave. They actually have a lot of energy according to its size, and we don't know where it is. But we can make some estimations of where these things are, and this is where the concept of orbitals come in. So an orbital is basically a volume of space around a nucleus. And from where we get this information on is from experiments dealing with light and energy of elements. And when the electron is in the atom, it has a specific energy. And when we add energy, these electrons actually gain the energy. And it's always in a specific amount. They gain a certain amount and they lose a certain amount. And when we talk about these gains and losses, they're related to like a steps in a house or on a ladder. The ladder steps are certain space, certain distance apart. And you put your foot on the step of the ladder, you move your foot so much higher to put it on the next step. You don't go into the middle, because usually when you try to do that, you'll go down to the bottom. So energy, electrons move up and down and gain energy in certain quanta or packets of energy. And this is what we mean by energy, is quantized. It means we have little packets of energy that electrons can move up and down. If we add a little too low or too high, the electrons do not move. And that brings a very interesting concept, and it makes chemistry very interesting. Now, when we talk about where are the electrons, we hypothesize to exist. They move around the nucleus in a particular volume, and this volume could change based on the energy of the electron. And when we talk about these volumes, it's basically we're looking at a probability that, say, in a sphere, we know that we can find 95% of the time we can find the electron. So we're looking at probability now. And then for each volume of energy, it has particular potential energy associated with it. So these electrons, we know the exact amount of energy associated with it. So we're going to end up saying in this sphere of around the electron, around the atom, we know we can find the electron 95% of the time. So let's kind of draw this out. So what we have a sphere, and the electron is basically running around here. Now the electron will not go into the middle of this. So if I redraw this, here's my positive protons. We cannot find the electron any closer to this, or maybe a little, but it's going to be somewhere out a little farther. And the electron, we got 3 electrons. These electrons are going to be anywhere moving around this nucleus. And it ranges from here to about here, and it's somewhere in between. Do we exactly know where in this realm, this volume of space? No. We have no idea where it is. But we know 95% of the time we know it's somewhere in here. The other 5% we don't know. But 95% of the time the electrons are going around here. So this is what we mean by the volume of space. And we call this the electron cloud. And sometimes electron could be many different volumes can be existing in here with different energies. And that comes to a little bit later on when you go to college. But this is what we mean by where the electron is. It is a probability. And what we have is that we're going to figure out what that probability is. We were given is actually a set of quantum numbers. And it tells us the energy and the volume of space the electron has. And each electron has a set of 4 quantum numbers, and they're unique for each electron. It's like an address or a computer address in memory. There's particular addresses that the electron can have, and no other electron can have that address. So quantum numbers is the way we describe the energy and volume of space. And we're going to be talking about 4. And the first one we're going to talk about is energy level. So these first quantum number dictates the energy level. And they're actually related to the row of elements on the periodic table. So the first row on the top is energy level 1. There we go, energy level 2, energy level 3, and so forth. And the energy of the orbitals are actually dependent upon the number of protons in the element. So if we only have like 3 protons, it's going to be in the second energy level. We can't have anything above 2. We can have a first energy level, second energy level, and that's it. And so that's one thing we need to realize, is that when we talk about these quantum numbers, we say the first energy level, all elements have a first energy level. Hydrogen and helium have a first energy level. They may not have 2, but lithium through neon has 2. So 1 and 2. And this is what we mean. It builds up. So this is the principal energy level. And then we'll go to the second quantum number. And it's basically what we call angular momentum. And lowercase l, and this looks like a 1, but I usually write it like this, signifies angular momentum. And for L, it ranges from 0 to n minus 1. So if n is equal to 1, L is equal to 0. For n equal to 2, L is equal to 0 and 1. I should say, or 1. So an electron can have an address for 2, 0 over 2, 1. Can have either one of these, and we'll talk about how do we get those later. But this cannot be 0 and 1 at the same time. It's either 0 or 1. All right, and this is what I mean. Also, the L's actually give us the type of orbitals. The s orbital is a sphere. I'm going to just draw it as a circle, and this is an s orbital. So anytime. And this is wrong. So this is 0, this is 1, this is 2. The slide is wrong. Sorry, you guys. I keep forgetting to correct that. So 0, 1, and 2. These are the slides. This is the L number. So L equals 0, we have a sphere. When L is equal to 1, it is what we call a dumbbell shape. Or an infinity sign or figure 8. And this is what a p orbital looks like. We calculate these out using high-level mathematics, and this is the results of these calculations. And d orbital, we have a clover leaf. And we've got 4 lobes, and this is what a d orbital looks like. So, and if L is equal to 3, we have f orbitals. And we do have elements with f orbitals, and I'm not going to draw those because I'm not talented enough. So let's go to the next slide. This is the magnetic quantum number. And this is what we mean by magnetic, and it has magnetic momentum. So when we have electrons that have in an orbital that has angular momentum, and the orbital is spinning, not the electrons are always spinning. Now the orbitals are going to be spinning. So when L is equal to 0, that s orbital is not spinning, but the p orbitals are. And when we have these p orbitals spinning now, and electrons are in there, we're actually going to have magnetic momentum associated with that. And so these electrons are splitting up these the p orbitals into 3 different groups or suborbitals. And the n quantum numbers goes from -1 to 1, or minus L to L in increments of 1. So if L is equal to 0, magnetic number is 0, but L equals to 1, the magnetic number is -1, 0, and +1. So we end up adding that out. So if L is equal to 2, the m numbers can be -2, -1, 0, 1, and 2. And we call these orbitals degenerate. They mean they're identical energy, not the other term. Thank you, folks. So this is what we have with magnetic momentums. And let me talk about this. Let me show you this. So if we have an s orbital, this is L is equal to 0. M has to equal 0. And it's going to stay like this in one line. Now I'm going to move up. We're going to add some angular momentum, the p orbitals. L is equal to 1. But it's not just one line, because there's 3 different ways we can take this p orbital and split it up. So in a magnetic field, they split up into 3 different orbitals, suborbitals, and this is going to be -1, 0, and +1. And this is by convention, by the way. Always start with a negative value. Always start with -1. So -1, 0, +1. This is what these p orbitals are. And they're 3. And we also call them X, Y, and Z, or Z. So this is what the designation of each of these. So if we add more angular momentum, the orbital spins a bit more. We have a D, L is equal to 2. And now we have 5 different suborbitals, -2, -1, 0, 1, or 2. Now, an element can have all of these 3 things if they're in the 3rd energy level. If they're in the 4th energy level, they're going to have these 3 plus another one, the f orbitals. Hopefully that makes a little bit of sense. Now the fourth quantum number deals with what we call electron spin, and it's either plus or -1/2. And so when we talk about plus by convention, +1/2 is up, and positive spin, and that's always first. That's negative spin or down, and this is last. And we'll talk about how the configuration of electron configurations in next lecture. And so what we have is a quantum number set that looks like this: 2, 1, -1, 1/2. This means that the electron is in the 2nd energy level in a p orbital of -1 magnetic field, and a spin of +1/2. And that's what we're talking about. And this, folks, we're at the end of our lecture. Like a little long, but hopefully take notes, and I'll see you guys later.